So in previous videos, I covered like a brief description of the CAN bus, connecting using an Elm device to an ECU, then doing some basic communication, and then pulling back all of the data from the ECU for my particular ECU. But in this video, I'm going to show converting that code into a graphical interface, or at least the very start of the code. There's still lots of stuff that I need to do. But if I run it here, I'm running it over secure shell on the Raspberry Pi, so the updates to the display won't be as fast as actually watching a screen connected to the Raspberry Pi, which I'll do in the next video. So when I do a next update to this graphical interface, I'll run it on an actual device, and I'll describe the device which I'm running it on as well. So it connects automatically to the Raspberry Pi, and it brings back just the Elm 327 device information on the first screen. So I've got a list of, or a series of buttons at the top of the screen. So this is the Elm 327 button. Then if I go on to the next button, vehicle, and then it'll bring back the information about the vehicle, which is mode 9 information. Basically, it's bringing back from the PIDs. And then the next button along, if I click on that, it goes trouble. So this is the trouble code information. So it brings back the trouble codes and converts them into the description so you can see what they're doing. And also at the top of this display, it tells you about the mill information, so whether mill light is on, and tests it does, which I believe it does when the car engine is running. The ECU will run tests on it and check for things like fuel system issues or misfire issues or catalyst tests. And they'll say incomplete at the minute because this is on a test rig on my bench and it's not on a running car. The next button along is plots. Now this is something I still need to do. I haven't done anything with that. Then freeze frame data, which I haven't done anything with that. And then frame, so this is like a frame of data. So it brings back all of the information from the ECU that it can get back. And the next button along is meters. And then if I click on the add button, which is the second button from the right, I can add a meter. And it shows me live data. So if I move my adjustment on my test rig, you can see the actual value adjusting on the meter itself. But on this meter, there's a drag button where I can move it around the screen, and ultimately I'm going to be able to add and as many of these meters as you want on display, well, within reason, because it can only communicate so much in a particular time period, and then be able to arrange them how you want on the screen. Then I haven't implemented the lock button, but when the lock button's pressed, these buttons on the top of the gadgets, they'll disappear, and it's just so that you can't accidentally drag them around. But there's a select button which I haven't done yet, which is where you'll be able to select the PID that you want. So I've hard coded this at the minute for engine coolant temperature, and then there's a switch button, so I can change the style of the actual thing to horizontal or vertical bars, or just text, or the dial gauge, so you better swap those around. Now I still need to do a bunch of stuff with this, so I need to make graphic buttons on them. There's a few buttons which I need to implement and some tidying up I need to do, but it's well on its way to being the graphical interface. I'll describe how the software works after this. If I click on the exit button now, and it comes out of the application, and so I'll go on to describe how the software works now. So these are the Python classes in the application, and I'll work from the bottom to the top. So at the very bottom there's a visual class, and this contains all the common elements and methods which I'd want for an item which I want to display. So like the location of the item at the X and Y coordinates, and the width and the height of the item. And it also contains the ability to handle displaying text on the visual item. So that's the basis of most of the things which are going to be displayed. And that's a superclass of gadget. So gadget subclass is the visual item. So gadget automatically gets the ability to display text and to be located on the display, and how wide and high it is. And gadget displays ultimately a piece of data in a visual way. So it can be one of many visual ways, a dial, or a horizontal bar graph, or a vertical bar graph, or just some text. And a gadget can have a button on it, and button is also a subclass of visual. So button gets all of the ability to display text and the location on the display. And so that way, with the visual item, separated out into a class of its own, you don't have to write that code twice. So that's common across several classes. And the button can also be displayed on a gadget, but it can also be displayed on the display. So that's a class above that. And the display handles like a desktop area. So it has common buttons across all of the items which are on the display all the time. And then it handles ability to move between kind of tabs. So you've got different things in different tabs. So you might have meters or data login or frame data or trouble code data all on separate tabs. And then just across to the right, there's the plot stuff, which I haven't done yet. It's data login, but it won't be great data login because OBDII doesn't actually communicate particularly fast because it's quite a low priority on the CAN bus, which makes sense because the ECU should be concentrating on running the engine. So the OBDII communication isn't particularly quick. But it should provide data login of some use. And then at the very top, the main application. So there's one display on the main application, and the main application decides how it wants to display information and tells the display on what elements which the display contains, where it wants to display the information, how it wants to display it. And then separately, completely separately, is the Elm 327 class, and that handles the communication with the ECU over the CAN bus, and that's independent of every other class. So the main application decides what data it wants from the ECU, asks for it, and then once it's got it back, the main application then tells the display how it wants to display it. So that's the kind of hierarchy of the classes which are in the application at this point. I'm going to go for the source code. I'll skip over a lot of it. I'll just pick out the bits which are kind of most important. I'll go through it in the same order or similar order I went through the class structure in. So this is a visual class. So this doesn't exist in its entity by itself. It's always a subclass from another class. So it just gives a basic stuff like attributes for position, name, size, text size and text alignment. And it can do things like you can get the name from it, you can set the position, set the text. And this is kind of one of the things which gets passed down. So is event. So from above, from the sourcing from the display class, you get messages coming down saying a mouse was clicked or a key was clicked or a mouse was moved, and it ultimately comes into here, and it's up to a particular element of the display to say, oh yeah, that hit me and I've handled it and this is what I did, or to say actually that was outside my bounds and it didn't affect me at all. And so the programmer just can decide what happens depending on whether things that get clicked on or missed. And then the last main thing is the display. So the display in the visual class will actually handle, it'll get a surface. So I'm using the interface called Pygame, and it has things called surfaces. That's very similar to a lot of game programming. So on the Windows DirectX, you get surfaces which you draw on, and in sort of other area, things like Java, you get surfaces which you draw on, which aren't actually the display, and then you tell them to now render this surface onto the display later. So in the display function or method, this is where we just handle doing graphical things to display what we want to display. So if I then go on to plot, so this class I haven't implemented yet, but I've still said it's going to be a subclass of the visual class, and it handles if an event happens, then it'll handle that. But as you see here, it passes the event down to the visual event as well. So the visual event can do what it needs to do with any kind of clicks as well. So so you can pass messages down into the superclass of this class, and it handles display. So all visual things should handle is event and display. And if they don't, then it will automatically go down to the visual classes function. So if a class which subclasses the visual class doesn't handle it, so if this function wasn't here, it would automatically just go down straight down to the visual classes function, handle it there. but the plot hasn't been implemented yet in my code, so there's not any more code in there. Button class is a very simple class. All it does is it handles events. So if a click happens on the button, it'll do very basic handling of that, and it displays how it is on the display. So it actually just displays itself as a rectangle. I'm going to need to update this to be a bit more graphic, and then it will then display what's in the visual class. And now the visual class displays text. So the button doesn't display the text, but the subclass of the visual class actually displays the text on the button. So that's where you save code in. So if you want to display text, then basically the subclass would display that. And then the gadget, which is a bit more complex. So in the gadget, there's different styles which you can display a gadget in. And the gadget has buttons on. So it will display buttons itself. And I've handled each gadget having a set of attributes, so I can define the attributes up at the top. So if I want to change any colors or anything, all I have to do is change the data structure at the top. And I could even load this in from a file if I ultimately wanted to. So all the attributes are set in the constructor, and then it recognizes a PID and PID number and PID description, which it's going to display, and also the value which it gets from the right at the top of the main application class. It will tell it a value which it wants to display. And then just at the end of the constructor, it sets the default style, which is gauge, which is like a visual, like a dial gauge. And it just handles events. So for clicking on certain buttons, like if you want to switch the style, you can handle the switching of the style. Or if you drag the gauge, it will drag it across the screen, handle dragging across the screen. This is all very simply done in like very small amounts of code, because it's not very complex stuff to do. You can get the application can request what the PID is that a particular gauge is displaying, or the application could tell it, I want you to display this PID, and then it sets the data separately, which we'll see when we get to the main application. Then you can change the style to whichever style you want to change it to, and then the display of the gauges is slightly more complex. It's just like any other display, but I've got a condition here, so depending on which style is selected, it will display the appropriate graphics for that style. And then the display, which is this class is a bit like a desktop. So I set up a bunch of container type things which I can consider to be equivalent of kind of tabs. So I want to display different information on different parts of on different areas, so you can switch between the different areas. And then I set the default tab to be the Elm one, because the first thing it's going to do when the application starts is automatically try and connect to the Elm device, and so it will display information there as it goes. Then the constructor initiates the display stuff for the Pygame. It does various things and sets up a set of buttons which it's going to display for itself. So things like lock, which I'm going to handle being able to, once the gauges are displayed as you want them, if you click the lock button, then all the buttons on the gauges will disappear and they'll be set in place, so you can't accidentally drag them around or switch them. Then the add button is to add the gauge to the meters tab. The mill light will hopefully I'll be able to get that to light up if the mill indicator occurs whilst the application is running. And then we've got the different buttons to select the different tabs on the display. I'm also displaying the date and the time, and I display that in a button. So a button doesn't have to react to a click or anything. It can just be used to display some text, as it's a subclass of visual, and visual displays text. And I've just got an exit button to exit the application. And then I set up tabs with the buttons I want to have on the tabs accordingly. The handle closing the application. All I'm doing is setting the mouse to visible again, because this is going to work on a touch screen display. It handles events, and it just decides what button's been pressed and what it needs to do. So it sets the current tab to meters, or if the frame button's been pressed, it sets the current tab to frame. So it switches through the tabs depending on what you want to press. And then it can also do gadget. So on the gadget, on any particular gadget, there's different buttons, but a couple of them are handled in the actual gadget itself. But this close button is handled by the application, because the application is what created the gadget in the display tab of meters, and so the application can actually then remove that if you hit the close button on a particular gadget. And then we can set things like text, and we can also do, it has the display function, and the display function raises the display, displays all the buttons it has, and then displays all the gadgets, and the gadget displays all the buttons on the gadget. And then this flip takes this surface, which is a Pygame surface, and puts it on the actual display itself. So the update happens really rapidly, so there's no like flickering of the display. And that's the display class. This Elm class hasn't changed at all since the last video, so if you want a description of how that is, take a look at the last video. And then the main application class. So create a lock. So when I'm communicating with the Elm device, I don't want more than one communication to occur at any one time. So if someone starts off a display frame data, I don't want them to switch then to the tab and be able to start communications asking for tab data, because the data will clash. And so only one communication with the Elm device should happen at a time. So we use this thing called the lock. I'm going to set up the classes which I want the application to have. So I've got the Elm class and the display class. And the display class will then contain gadgets and buttons, and gadgets will contain buttons. Then I have a set of functions at the top of the application before I actually get to the application itself. And these all do the communication that's required with the Elm device. Now the lock was there because I'm using multi-threading, because if it came into this, say this function to connect to the Elm device, and it started communicating with the Elm device, these things where I'm setting text, they wouldn't get updated on the display if I wasn't doing multi-threading, because it would be in this thread and it wouldn't get to do the display until it came out of this thread. So this thread is communicating with the Elm device. Then meanwhile, the main thread can be updating the display. So when I'm setting this thing like text saying connecting to the OBDII interface, then that text will get updated on the display. So the user isn't sitting around thinking, is this connecting or isn't it not? So the user can actually be getting updates whilst the communication is going on. So these set of functions at the top of the application, these all do the communications, and then at the end they're responsible for unlocking the Elm lock, so that then after they've finished, another Elm request can occur. And so they all do. So this one gets frame data. The first one connected to the Elm device. This one gets vehicle data. This one gets the related trouble code information and displays it. This is to do with clearing the trouble code. So there's a button to clear trouble code if you want to do that. And this one gets data related to meters for gadgets. So when you add gadgets, so you can add like 4 or 5 gadgets. I only showed display adding one because I haven't put the code into select which PID is related to that gadget yet. But when you display 4 or 5 gadgets, this function will actually get the values for those gadgets and update the values in the gadgets. And then when it comes to display them, you will get displayed up-to-date information then. Okay, so this is the actual start of the application itself. First thing you need to do is acquire a lock. Now it's not actually locking it at that point. What it's doing is from the operating system, it's saying, give me a lock which I can use so that when I want to lock and unlock things, I can then use it to do that. So that's just acquiring that. And then Pygame has a timer, which I'm using to do things like update the dates and time on the display, and communicate with the Elm device. I think, oh yeah, that's right, for the meters, I'm getting the data from the meters every 2 seconds. And then this is the main application loop. So most operating systems operate on this thing called the message loop, where you get messages and then your application reacts to them, and that's all this is doing. And so Pygame will send me a set of events type thing, and so one's a timer event, so that's where we do the update of the time and date, and then we update the meters data by calling. So what it does is it acquires a lock. If it fails to acquire a lock, then it won't get meter data, but if it manages to get the lock, then it'll go off and do the meter data. So if there's already a lock because something's already using it, already communicating with the Elm device, this makes sure that we won't automatically start another thing communicating with the Elm device. And then for most of the operating system stuff, I don't handle it unless if there's a communication currently going on with the Elm device. So for example, if we get quit messages or key down messages, I ignore them. So basically the only thing that I'm doing whilst an Elm communication is going on is updating the time and date, and then, well, I'm checking to see if I can update the meters, but I can't because of an Elm communication occurring. So I'm just really updating the display and updating the time and date. So the updating of the display occurs at the end of this. But if there's no lock enabled, then I check for key presses, and I do things like exit the application or adding a gadget to the meters display, or handle other buttons like connecting. So I'll start. These are the communication things like changing tabs, so it communicates with the Elm device to update the display on each particular tab. And then I handle mouse up events. I think the application actually doesn't do anything with mouse up events, but it's there for if I need it. And then mouse motion is to do with dragging gadgets around, so I handle doing that. And then this is where it does the display. So it can do this, it can update the display, because when I'm communicating with the Elm device, it's doing it in a thread of its own. So this update display always occurs even when I'm communicating with the Elm device, which is a good thing. And then it falls out the bottom if I get a quit command. And that's the basic overview of the software. In the next video, I should have the software run on an actual device, on an actual Raspberry Pi with a display, touch screen display, and hopefully I'll have a lot more graphics on the graphic display as well.